Hello class, this lesson is on the amount of an annuity. An annuity, what is an annuity? It is a series of equal payments made at regular intervals. So it's a little different than putting money into the bank and letting it earn a small amount of interest. This is an intentional investment strategy where you're putting in money maybe every month, maybe every 2 weeks when you get paid, maybe semi-annually when you happen to have a little bit extra after a tax return, maybe annually. In an ordinary simple annuity, this is important, payments are made at the end of each compounding period. What that means is that the amount that's in there at the beginning of the compounding period will earn interest, and then at the end of the compounding period, an additional deposit is added onto that. And an annuity is just a series of regular payments. The amount of an annuity is what you get when you total up what all those deposits plus interest are worth. We've done simple interest and compound interest previously. You had a chance to review some of these questions on the Activate Prior Knowledge section, pages 406, 407. In this lesson, I'm going to go through the Investigate, which you find on page 409 of your textbook, called Determining the Accumulated Value of Regular Deposits. So here we have a $1,000 deposit made at the end of each year for 5 years. The annual interest rate is 6%. It's compounded annually. Now remember, when interest is compounded, we have a compound interest formula. An amount of interest, the investment equals the principal amount multiplied by your interest rate plus 1 to the exponent n, where n is the number of compounding periods, a is the amount of the investment, and p is the principal. A is sort of what's called a future value. It's what happens after you begin with your principal, and in the future it's worth a little bit more due to compounding. This is an exponential relationship. The growth factor would be the 1 plus I value. I is the interest rate as a decimal. N is number of compounding periods, and in the case where your compounding is not annually, you need to make sure that you take your annual interest rate and you divide by the frequency of compounding. The frequency of compounding would be once annually, twice semi-annually, 12 times monthly, 52 times weekly, etc. So this depends on how often it's compounded, and it's always stated in the question. So if it's annual compounding, that's once a year. So we don't need to adjust our interest rate. Now, when we calculate an annuity table, which is what we're doing here, we have a couple things to consider. We have the rules for a simple ordinary annuity, which is that deposits are made at the end. Each deposit earns interest for just that 1 year, and then the interest is added on to the previous balance. So in the first year, no interest is earned because there's no money in the account. Starting balance is 0. At the end of the year, a $1,000 deposit is made, and that would be the ending balance. To start year 2, we have $1,000 in the account. Now this $1,000 is going to earn interest according to the compound interest formula. Principal would be the starting balance. We calculate amount by taking that and multiplying by, in this case, 6% interest. Our interest value would be 0.06 added to 1. 1 plus I will be 1.06. The n that we're going to use here is for a 1-year term. So we're just calculating the amount that that $1,000 grows to at the end of that 1 year. So it would be 1,000 multiplied by 1.06, earning interest all year long, and that would give you 6% of $1,000 is $60, which means that at the end of that second year, that $1,000 starting balance has grown to 1,060, which means we earned 1,060, take away 1,000, or $60 of interest. to calculate interest, we take the amount and subtract the principal as shown above. The deposit again comes in at the end of that second year, earning no interest, but it's there in the account now. So collectively we now have $1,060 plus $1,000. So we have $2,060 at the end of the second year. That will be our starting balance for year 3, 2060. So 2060 comes in as the principal for the start of year 3. It's going to earn interest according to the compound interest formula. Now our principal has grown considerably. 6% is applied to that for 1 year, and we can calculate the remainder of this annuity table in the same fashion. Now, at this point, we're looking at the completed annuity table. We've carried forward our balance 4 times, and in each case we've calculated the 1 year amount, including interest. We've subtracted off the starting principal balance at the beginning of the year to determine how much interest was made in that year. And I'm just going to circle these values here. So this isn't total interest to date, this is just interest earned. You can clearly see that the amount of interest earned just keeps growing, and it's growing exponentially because the balance is carrying over. And so we're calculating 6%, which is a growth factor, on a larger and larger value. The deposit always adds an extra $1,000, which increases the year-ending balance, and it also increases the starting balance. So final value of this annuity would be $5,637. Now we can get at the amount of interest that we've earned in a couple ways. We can total the interest column, and the total of these 4 interest values will give us the total interest. We can do that now. So the 4 values there give us a total of $637.10 worth of interest. Now you can look at that number over here and see that value as well, because the interest here would be a simple matter of taking the final amount of the annuity, which is the total of all the deposits, including interest, and subtracting off the number of deposits that are made. And in this case, I'm introducing some notation here. There were 5 deposits made, so there were 5 terms in this annuity. R is the value of the regular deposit, and capital A is the amount at the end for all of the interest plus principals. So really what we're doing there is we're seeing that we had $5,637.10, and how many deposits were made? Were 5 made. The deposit value was $1,000, so we deposited $5,000 here, and we ended up with $637 additional from our investment. So that's another way of getting the 637.10, and it's accurate here because I've rounded to 2 decimal places for pennies all the way through in these values here. But even with that rounding, we're still able to be accurate to the nearest penny in this case. So this is the annuity table. Now this is not commonly how people calculate the amount of an annuity. We want to move forward from this, just understanding the process. It would be very tedious to do this process for, say, 10 years for something compounded monthly. We'd have a lot of terms. We could use a spreadsheet, a computer spreadsheet, to calculate this for us. We've got the general idea of what the formula is. We could repeat that formula many times in rows and columns of a spreadsheet. That would be a quick way to generate the annuity table. We can now, from here, move on and look at some of the properties of an annuity. So an annuity has a formula, which is the sum of all those terms, each earning interest for that 1 year amount, or maybe in a different annuity it might have been monthly. So the formula for this is found in your textbook on page 411, and here's the formula. Capital A is the amount of the annuity. R is the regular payment or deposit. I'm going to put brackets in here to separate out a couple things. One is looking a little bit like the compound interest formula, 1 plus I to the n, subtract 1 divided by I. This is how we calculate the amount of an annuity. So R is the regular deposit in dollars. I would be the term interest rate as a decimal. And N is the number of payments or number of periods of compounding, which for an ordinary annuity, ordinary simple annuity, should match the number of payments as well. So in our example, we had 5 payments. The regular deposit was 1,000. The final amount was 5637.10, and interest rate was 0.06. Now, just so you have an idea of what's going on in this formula, we could start with an arrow diagram to show that if we began with our interest rate and we want to end up with the amount of the annuity at the end, first thing we have to do to the interest rate is add 1. Then we're going to take that and raise it to the exponent n. The result of that is going to be reduced by 1. The result of that gets multiplied by r. The result of that gets divided by I. And that produces the amount starting from the interest rate. Okay, so at that point, it sets us up for calculating, if we wanted, potentially solving for the interest rate if we had the amount. A little bit difficult to do because the interest rate appears twice in the formula, but it does show the steps. When you calculate this, you need to make sure you follow order of operations. So I'm just going to repeat this calculation for our previous example here. We had here already identified that R was 1,000, N was 5, I was 0.06. So I substitute my values in here. Take my time to just work out the power. Then I subtract 1. Then I multiply by 1,000 and divide by 0.06 at the same time, and I end up with my final answer here, which all pretty much confirms what I had determined from my annuity table when I did this the long way. And I even have a penny difference, which probably suggests that my rounding in my table just caused a little bit of a difference. So when you carry forward your decimals here, I would suggest carry forward lots of extra decimals, because when money's on the line, people don't want to be deprived maybe of a small little bit, because over time it could add up to a large amount. So in this case, rounding it to the nearest cent is sufficient, and it just goes to show that when we have the information ahead of time, we can use the formula as an alternative to working this out, and it's much more convenient. And just make sure you follow the steps in the arrow diagram. As you move forward in this activity here, you're going to discover also that technology can be used to solve annuity problems. Now I'm going to show what's called the TVM solver, or the time value of money solver, on the graphing calculator, and it uses 8 quantities, and we put in the values similar to what we did in the formula, following certain rules, and then it will calculate for us the future value or the amount. So the special format, or the rules for the time value of money solver, is that number of payments is n, I is the annual rate, so don't need to adjust that for the frequency if it's compounded multiple times a year. PV is the principal or present value at time 0. What do we have currently? PMT would be the same thing as capital R in the formula. It's the regular payment or the deposit. In the case of the future value is what it amounts to in the future. P/Y is the number of payments you're making per year, or deposits per year, and C/Y is the number of compounding periods per year. That could be different. An ordinary simple annuity, they have to be the same. PMT is the just where we get to specify if the payment or the deposit is made at the beginning or end of the compounding period. For an ordinary simple annuity, it's made at the end, but the TVM solver is versatile. It would allow us to explore different situations. So we can use this solver here now to enter in some values. The only other thing we need to know is that if we're paying out money, if we're contributing to an investment or making a payment on, for a loan, that's money that we're paying out, that would be a negative value. If it's money coming to you from an investment, it would be a positive value. If you at the start don't know the value for the present value or the future value, just enter 0 if it's not known or if it's not being used in the problem. So when we turn on the calculator, we're going to go to apps, and you may have multiple apps in your calculator. We're going to choose app number 1 and the TVM solver off that. Here we have our special quantities that we need to put in. So remember, we made 5 payments, so n is 5. In this case, the interest rate was 6%. Just leave it as a percent. It'll convert it for us into a decimal. The present value would be 0 because we start out with no balance. The payment is $1,000, but it's money that you're paying out, so it's negative $1,000. It'll come back to you afterwards, but that's a payment. Future value, we don't know it currently. We're going to be using it, so for now we can leave it as 0. And the payments per year and compounding per year, it's both annually, so we leave that at 1 and 1. Now we go down here to payment, and we have the option of beginning or the end of the period. We'll leave it at end. And we'll go back up to the quantity that we're trying to solve for, and we'll press alpha enter. Alpha enter is going to solve for us, and you see this in your textbook. On page 413, it'll go through the use of the TVM solver for example 3. So alpha followed by enter is going to give us our future value or the amount of the annuity at 56.37 and 9 cents. So notice that's a positive quantity because that would be money coming back to us at the end of those 5 deposits. So that's how you use the TVM solver to calculate the amount of an annuity. Okay, the final part of this worksheet here that you're filling in is just listing applications of annuities. So why do people make regular deposits? Well, for obvious reasons, you're trying to save some money. So you might be saving money for a future goal. Could be a car, could be a down payment on a house, could be a vacation, could be a snowmobile, something like that that you want to save up for. Or maybe you have an educational goal or retirement goal. Making small but regular deposits of money can accumulate to large amounts of money over time, we read in the textbook, and the proof of this will be worked out in some of the problems where you'll see the impact of delaying investment and also the impact of finding a better interest rate or finding a higher compounding frequency. And all those things will be explored as we go throughout this chapter, just to give you good financial literacy when you get out into the world of work and you're making an income. What do you do with your money besides just spend it on the things that you need throughout the week and throughout the month? Setting a little bit aside is a good practice so that you'll have an amount in the future to look forward to draw on when you need it. So you can see the assigned questions here that we'll be working on in class. At this point, the examples in the textbook provide additional support for you to see how the formula works and how the TVM solver can be used. And you'll be relying heavily on the use of the formula as well to solve most of these questions, including comparing retirement plans. So at this point, we'll close off the video and we'll see you in class next period.